Hey folks, welcome to another set of AP Chemistry video notes. Unit 2 is all about the structure and properties of molecular and ionic compounds. Today we're going to cover the first 4 topics in Unit 2, which ask you to explain the relationship between the properties of the elements participating in the bond, represent the relationship between potential energy and distance between atoms based on factors that influence the interaction strength, represent an ionic solid with a particulate model that is consistent with Coulomb's law and the properties of the constituent ions, and represent a metallic solid and/or alloy using a model to show essential characteristics of the structure and interactions present in the substance. In learning these 4 topics, the overarching goal is for you to learn that atoms or ions bond due to the interactions between them, forming molecules. So let's get started. Topic 2.1 is about the types of chemical bonds. In order to really understand the different types of bonds, you must know the periodic trend for electronegativity. Fluorine is the most electronegative element. From there, electronegativity decreases as you go down a column or towards the left in a row. It's important to not just memorize this trend, but understand why electronegativity trends this way. Electronegativity is the ability of an atom to pull shared valence electrons toward it. A higher electronegativity means that it can pull harder on these shared electrons. The trend for electronegativity is explained in the same way that you might explain ionization energy. As you move from left to right on the periodic table, you increase the effective nuclear charge of the atom, which pulls harder on the valence electrons. If the nucleus is able to attract the valence electrons with a greater force, then it has a higher electronegativity. As you move down a row, you add principal energy levels, or shells of electrons, pushing the valence electrons further from the nucleus. According to Coulomb's law, the further the 2 charged particles are from each other, the less attractive force there is. So the bigger the atom is, the less able it is to attract shared electrons. In other words, the less electronegative it is. Now that we understand electronegativity, we can talk about how that affects the type of bond that forms between 2 atoms. If the 2 atoms have very similar electronegativity values, neither atom will pull harder on those bonding electrons than the other. If both atoms are pulling equally on the bonding electrons, this is called a nonpolar covalent bond. Polar, like the north and south poles of a magnet, just mean that there's a positive end to the bond and a negative end to the bond. If it's nonpolar, that means there are no positive or negative sides to the bond. If the electronegativity values are not similar, that's considered a polar covalent bond. Whichever atom has a higher electronegativity value will pull the negative electrons closer to it and develop a partial negative charge, symbolized by the lowercase Greek letter delta with a minus sign as a superscript on it. The other atom, then, will form a partial positive charge because it doesn't feel the effect of those negative electrons as much as it normally would. This is symbolized in the same way, but with a plus sign for the superscript. For all single bonds, the larger the electronegativity difference between the 2 atoms, the greater the partial negative and positive charges will be. These partial negative and partial positive charges are called dipoles. An important thing to note is that all polar bonds have some ionic character. We often look at a chart like this one, which has clear cutoff values for the electronegativity differences and whether that bond is polar, nonpolar, or ionic. In reality, this is more of a continuous spectrum. As you increase the electronegativity difference, you increase your ionic character and decrease your covalent character. You can't just look at the electronegativity values, though. In general, when 2 nonmetals form a bond, that's considered a covalent bond. Even if the electronegativity differences are greater than 1.8, if both atoms are nonmetals, it's considered covalent. If one atom is a metal and the other is a nonmetal, that's usually considered an ionic bond, even if the electronegativity difference is less than 1.8. Our last type of bond is metallic bonding. When atoms of a single metal or multiple metals bond together, they don't generally form distinct bonds like you'd imagine with a covalent bond. The nuclei of these metallic atoms form a lattice-like structure and are held together by what we often call a sea of electrons. That really just means that those electrons are delocalized, or in other words, they're not tightly held onto by any one particular atom. Topic 2.2 is all about the forces within molecules and the potential energy associated with that. We can use a potential energy versus distance between atoms graph to represent this in a useful way. These graphs help us understand the bond length between two atoms and the bond energy. The bond length is the distance between two atoms. Specifically, when the potential energy on this graph is at its lowest point, that's the length our bond will be. So when we look at a graph like this, we look for the lowest point on the graph and determine its position on the x-axis. And that gives us our bond length. Bond energy is the energy required to separate the two atoms. We'll talk more about that in a minute. As you can see on this graph, as our two atoms are far apart, the forces of attraction between them are basically zero. When the atoms move closer together, their attractive forces increase. At some point, the attractive force reaches a maximum value, or a minimum point on the graph. This is the ideal distance between the atoms. If you push the atoms any closer together, they start to repel each other because of the positive charges in the nuclei. You can see that instance on the far left side of this graph, where the graph goes up significantly. So, as you can see on the graph, the energy required to break the bond is located here. This is an endothermic process because you have to put energy into it in order to break the bond. When you form a bond between two atoms, it releases a certain amount of energy. That's considered an exothermic process. The amount of energy released when forming a bond is equal to the same amount of energy it requires to break that bond. Endothermic processes have a positive change in energy because you add energy into the system, and exothermic processes have a negative change in energy because the energy leaves the system. When you look at the value on this graph, you see negative 7.24 times 10 to the negative 19 joules. This is the energy associated with one single bond between these two atoms. That's a really small number to talk about. So usually when we talk about bond energies, we talk about the energy associated with a mole of each of those bonds, not just one single bond. So to find the molar bond enthalpy or bond energy, you just multiply the value on the graph by Avogadro's number. This tells us that to break the bonds in 1 mole of this substance and cause the atoms to separate apart, we would have to add 436,000 joules. Alternatively, if we were to go in the opposite direction and form the bond between these two atoms, it would release 436,000 joules of energy. For covalent bonds, the length of our bond can also be influenced by how large our atoms are and what bond order we're looking at. The larger our atoms are, the more distance there must be between our atoms. If you have more distance, you have a longer bond length. These bonds are easier to break, meaning they have smaller bond energies. The bond order, whether it's a single, double, or triple bond, also affects the bond length. The higher the bond order, the stronger the bond, the shorter the bond, and the greater the bond energy. If we were to compare the following covalent bonds in each set, which one do you think would have the longest bond length? In the first set, we're looking at various hydrogen halide compounds. Remember, the bigger the atom, the longer the bond length. So which atom is bigger? Fluorine, chlorine, bromine, or iodine? Since we add shells of electrons as we go down the periodic table, iodine will be our largest atom here, making the Hi bond the longest of this set. What about these different carbon-carbon bonds? Remember, the higher the bond order, the shorter the bond length. So the single bond here would have the longest bond, and the triple bond here would be the shortest. Since ionic bonds are just attractions between charged atoms, otherwise known as ions, we need to think about Coulomb's law to really understand the interactions between a cation and an anion. The strength of the interaction between a cation and an anion is proportional to the charge on each atom. The larger the charges, the stronger the interactions. The interaction strength is also affected by the distance between the nuclei of the two ions. If that distance is smaller, your interaction is larger. The distance between the nuclei is determined by the size of the ion. So smaller ions lead us to stronger interactions because the distance between the nuclei can be reduced. So, looking at our examples here, which cation-anion pair in each set has the strongest attraction? For our first set, we have the same anion, fluorine, but different cations from the same family. Remember, as we move down the periodic table in the same family, our atoms or ions get significantly larger. Therefore, sodium would have the smallest ionic radius, allowing for the least distance between the nuclei of the two ions and giving us the strongest interaction. Generally, the charge tends to outrank the size when it comes to comparing these interactions. So, like we said, according to Coulomb's law, the larger charges will have stronger interactions. Therefore, the interaction between a 3 positive aluminum and a 1 negative chlorine would be significantly stronger than that of a 2 positive magnesium or a 1 positive sodium. Beyond understanding the interactions between the ions in an ionic compound, it's also important to understand the structure of an ionic compound. We often get used to working with chemical formulas, which work very nice for covalent compounds. Covalent molecules exist as distinct formula units, each particle having a set number of atoms within it. For example, every molecule of water has 2 hydrogens and 1 oxygen. We write the ionic compounds in a very similar way, but they don't actually represent what's happening. Even though we represent ionic compounds with a chemical formula, those compounds don't exist as distinct formula units. For example, sodium chloride does not exist as 1 sodium ion and 1 chlorine ion bonded together. They exist as a 3-dimensional crystalline structure. This formula in HCl is only meant to show us the simplest ratio of those ions together. The crystalline structure of an ionic compound is set up in a way that maximizes the attractive forces between cations and anions, while also minimizing the repulsive forces between ions of the same charge. Here are 2 models of sodium chloride. Model A shows you how the ions are arranged to maximize the attractions between oppositely charged particles. The smaller spheres here are sodium ions, and the larger spheres are chloride ions. Model B just shows you an expanded view of that. You can see the geometry a little more clearly and how each ion interacts with 6 oppositely charged ions in a 3-dimensional way. Since we're no longer talking about distinct molecules and bonds, it's appropriate to talk about the lattice energy instead of the bond energy. The lattice energy is the same concept. How much energy does it take to break particles away from the crystal lattice? When asked a question about this, you can use your knowledge of Coulomb's law and the strength of ionic interactions to compare and predict the relative lattice energies of different compounds. Last but certainly not least, 2.4 is all about the structure of metals and alloys. As we saw before, metallic bonding is usually represented as an array of positive metal ions surrounded by a sea of delocalized valence electrons. Most pictures you've probably seen of this show you what that looks like in a pure metal. Not all metallic substances are pure though. Some metallic substances are homogeneous mixtures of a metal and other substances. We call these mixtures alloys. There are 2 types of alloys, interstitial and substitutional. Interstitial alloys are those formed between atoms with different atomic radii. The smaller atoms will fill in the interstitial space, or the gaps, between the larger atoms. Steel is an example of an interstitial alloy, in which carbon atoms with a radius of about 76 picometers fill in the gaps between iron atoms, which have a radius of about 156 picometers. Substitutional alloys are formed between atoms of similar radii, where one atom will just substitute itself for another atom in the lattice, like in brass. Brass is a mixture of zinc and copper, approximately 142 picometers and 145 picometers respectively. Well, that's all for today, folks. If you have any questions, please don't hesitate to ask.